the quiz from last time, find and simplify the difference quotient for this function. You have to find the difference quotient. You have to write the definition, which is f of x plus h minus f of x divided by h. So please write it down if you didn't get 10 out of 10, so you may need to brush up on this. So the next step would be to replace x by x plus h. So this is x plus h plus 5 divided by what I would have done. I would have liked to do this first because it's kind of inconvenient to have that negative in there in the denominator. So I can put a negative outside. So then I have 3x plus 3h minus 2, and then minus, but when I write minus, because there is a minus in front, this changes into positive, so this is x plus 5 over 3x minus 2 divided by h. Do you have to do this? No, not necessarily. So the next step, I find the LCD, and the LCD is 3x minus 2 over 3x plus 3h minus 2. Remember, the denominator will not go away. These two factors will not disappear. Okay? When we put the limit in front, something's gonna change, right? But it cannot disappear. So this numerator needs to be multiplied by 3x minus 2. This numerator by 3x plus 3h minus 2. Because we cannot add the numerators without making those adjustments, right? So now careful, 3x, I start with the smallest, in this case from the binomial I distribute instead of the trinomial. It doesn't matter really. So 3x times x distributed to all three, keeping in mind that I have to change all signs. So this will be negative 3x squared, negative 3xh minus 15x. Then I distribute negative 2, but there is a minus in front, so I put plus 2x plus 2h and plus 10. This is just this product. Now, and you know I'm going to run out of room, obviously. So I distribute x to these three, so plus 3x squared plus 3xh and minus 2x. And now I distribute 5 to these three, and I'm going to write it here, of course. So 15x plus 15h and minus 10. At this point, I take a deep breath and I say, okay, terms without h must go away. It's a bonus if more terms go away, but definitely terms without h must go away. Okay, so let's look for those. These two. This is a bonus. These two. These two, and these two. So what is left is this and this. Nothing else. When I add those, I get 17h. So this is 17h over this denominator, 3x minus 2 times 3x plus 3h minus 2 times 1 over h. And I want to see you simplify these. There is no longer h in the numerator because this goes away. So this final simplified form is this. And this is final. Some of you had a minus and minus, which is okay. It's still the same thing. But we prefer eliminating those negative leading coefficients at all times. Yes, Derek, you want to say something? No. Okay, any questions, please? Is this okay, step by step? Okay, so please practice this. Please, that's very important. Okay, now the quiz from today. Any questions on this? Is this okay? Okay. So here's the quiz from today. I'm specifically told to simplify the function fully before I find the limit. So I disregard this symbol, and I have to start with the absolute value 1 minus x. So the absolute value of 1 minus x, by definition, is 1 minus x. If 1 minus x is greater or equal to 0, is negative 1 minus x, or 1 minus x is less than 0. So this is a definition that I apply It's a formal definition of the absolute value without calculating anything. So this is my first step. I applied the definition to the absolute value 1 minus x. That's all I did. No calculations. But now I will try to clean it up. It's not cleaned up. So the absolute value of 1 minus x, I don't have a problem with writing this as negative x minus 1. I'm cheating a little bit because I'm looking at the denominator. So I really want everything, not just that, but I always like everything in descending order and no negative leading coefficient. It makes my life easier. Okay, now I have to solve this. I move negative x to the other side, and when I read from here, be very careful. This means x less than or equal to 1. Again, I'm not saying you did anything wrong. I didn't even look. I refuse to solve the other one. If this one is less than or equal to 1, the other one must be the opposite, whatever the opposite is. I'm not going to waste my time and solve the second inequality. And now when I distribute here, this is nice. It's x minus 1. Now this piece is completely cleaned up. And now I have the absolute value of 1 minus x divided by x minus 1. And I know I'm going to have two options. One thing is for sure, this can no longer be 1 because this piece is in a denominator. So this can be less than 1. And the other one is correct, greater than 1. And now let's figure out what we have as the first option. The first option is when the top is negative x minus 1 and the denominator is x minus 1. What do I get? Negative 1. Excellent. The second option is when the top is x minus 1 and the bottom is x minus 1, and the answer is 1. Only now I can write the limit. I didn't even look at it. I don't even know what it says. I don't care. But now I will. Limit as x approaches 1 from the right. Which branch? Yes. And the answer is?
1.
We have at this point in time, we have to be able to simplify and easily manipulate these absolute value expressions. Don't worry about it. If you think that you didn't do very well on this, it's okay. You're going to have another option, another opportunity. Okay? But please make a note of this. Do not draw conclusions right away. Just say 1 minus x is greater than or equal to 0. No, just take it slowly, step by step, simplify it fully, and then put it back in the function. Any questions? Any questions? Is this okay? Okay. Now, any of these, did anything give you any, so we looked at this problem together, we looked at this problem together. Anything from those 8 problems? Anything? This was done in class. I think this was done in class also. Correct me if I'm wrong, please, anytime. And this was done in class. Any questions on anything? I'm sorry? Number 6, we just rationalize like we did last time with 1 plus h plus 1 over 1 plus h plus 1, of course, with the square root. Is that okay? Okay, anything else? Because we are going to add on today. We're going to add on number 7 and number 13 today in the next few minutes. Bless you. Anything? Anything else? Other questions for me before we continue with continuity? Bless you. You want me to, after you here a little bit? Maybe that's... Okay. Ready? Okay, so we go back to continuity. And there is a very important theorem that we are going to talk about in the next few minutes. But I would like to at least choose something like this. You're going to have a problem like this because the other group asked me about a problem like this. So I want to see when you get to it in WebAssign. And that's pretty much it. And then I'd like to explain the intermediate value theorem. And then we can continue. Ready? Any questions for me? Okay, so remember, let's refresh our memory on one topic from continuity, which is continuity at a point. Can anyone dictate the definition of continuity at a point? When is a function continuous at a point? When? Correct, but there is a definition that it's continuity at a point. Excellent. This is an extremely important definition. Continuity at a point. The limit from the left equals the limit from the right. They both exist. They are the same, and they furthermore equal the function value at that point. Excellent. So here is the following problem, 45, on page 129. Okay, so let's read it together. Let's see it first. So we're given a function. What type of function is this? Excellent. It's a piecewise defined function. It says for what value of the constant c, then these are flow parameters. For what value of the constant c, you see it here and you see it here, is the function f continuous everywhere on all real numbers. So I'm going to copy the function. So this is f of x, and this is cx squared plus 2x for x less than 2, and it's x cubed minus cx for x greater than or equal to 2. I would like us to, before we start, I would like us to talk about the theorem. Polynomial functions and others. I'm going to mention the other functions in a minute. Polynomial functions are everywhere. Polynomial functions are, what do you think? They're always continuous everywhere. I know it's redundant. The always is redundant, so you can skip it. But yes, polynomial functions are continuous everywhere. So then, this is my starting point. I'm going to write about this function first. Other functions are continuous on their domain, of course. I'm going to mention that. So I'm going to start by writing one, cx squared plus 2x and x cubed minus cx are continuous everywhere as functions. What are they? Exactly. So they're continuous everywhere. So there is no problem there. But where could the problem arise? At 2. So we have to discuss continuity at x equals 2. Awesome. That's it. What has to happen at 2 for the function to be continuous everywhere? Thank you. Right? Limit from the left of 2 equals to the limit from the right of 2 equals the function value at 2. Good. So now I'm coming back to the function. Please tell me, what is the left branch? Excellent. Thank you. What is the right branch? I know it's silly, but I'm waiting for you to. Very good. Perfect. And where is f of 2? Right here. Can anyone give us f of 2? Whatever it is. You can still give it to me. Excellent. Perfect. So now can anyone give us this limit? Can anyone give us that limit? What is this? Excellent. Excellent. What about this one? Good. So now how many parameters, how many unknowns, if you want, we have in this problem? Exactly. How many equations we need?
1.
Good. So can anyone give us the equation we have to solve that will give us C? That particular C and the only C that makes this function continuous everywhere. I'm ready. Excellent. So I move to C and I move 4. I get 6C equals 4 or C equals 2/3. I do have to go back and rewrite the function and say f of x guaranteed to be continuous on negative infinity to infinity. Of course, it means everywhere. So can anyone dictate how do I write the function? Very good. Plus 2x. And the second branch? That's it. Do you think that this function is continuous everywhere? We made it. Because we set a condition that the limit from the left equals the limit from the right equals the function value at that value, at 2. Absolutely. This is absolutely continuous everywhere. No questions. So here is my version of, any questions, please? Any questions? Everything clear? Okay. Intermediate value theorem. I like to present the specific situation that we are using all the time, but you can look at the general definition or general theorem. That's fine too. But really, we always change it into what I'm showing you in a moment. Okay, so let's take a look at a function. This is a function f of x. And I will write 2 different hypotheses. And you will tell me whether you accept them or not. Here's the first hypothesis. I would say that f continuous on a comma b. I'm not saying f is continuous everywhere. I'm only saying f is continuous on a comma b. Would you accept that? Perfect. Okay, so now I'm going to say this. F of a is less than 0 and f of b is greater than 0. In general, because it could be the opposite, f changes sign on the interval a comma b. Would you agree with that? It could be this, or it could be this, right? It could have f of a positive and f of b negative, or f of a negative and f of b positive. One or the other. In other words, f changes sign on a comma b. Would you agree with both hypotheses? So here's what I say then. Then it implies by IVT, intermediate value theorem, by IVT, there exists a C. Here it is. This is a new symbol, the last one I promised this semester. This is a new symbol that means is in the open interval a comma b, such that f of c is excellent. This theorem is extremely useful, but it has a flaw, a big one. It will not solve the equation for us. It will not tell us what it is, what's the solution. It will tell us you're looking for a solution. Okay, the solution is between 1 and 2. Because the function is continuous, otherwise I can't draw any conclusions. The function is continuous and it has to change sign on an interval. There must be, since it's continuous, it must cross 0, either coming from below or coming from above. It cannot jump over 0, coming from positive to negative or vice versa. It has to go through 0. But the theorem does not tell us what C is. It says, again, you're looking for a solution to the equation f of x equals 0. You're looking for a root or a solution or the x-intercept. Okay, look for it between a and b. What is it? I have no clue. But that is a huge step forward, because you'll see what happens in chapter 4. We will be able to solve any equation we want with calculus, but we don't have the tools just yet. But this is going to be the starting point, the intermediate value theorem for continuous functions, only for continuous functions. If the function is not continuous on the interval a comma b, the intermediate value theorem is not applicable. Okay, so please choose any equation. The interval here is given. In general, the interval will not be given. So let's choose one, whatever you want, with a given interval or not. But you will not be given the interval in general. You will have to look for one.
56.
Which one?
56.
56 it is. Natural log equals 3 minus 2x. And that is on page 129. And the equation, one more time, is natural log x. I think it's 3 minus 2x, yes. So I'm asked to solve this equation. First step, set it equal to 0. Natural log x plus 2x minus 3 equals 0. Step number 2, I denote this by f of x. In step 3, I find an interval a comma b where there is a solution. I don't know, but I have to think for a moment. I have to plug in numbers. I have to put the function in the graphing calculator. But I have to think for a moment, where do I start? 2x, nice and friendly. Negative 3, nice and friendly. Natural log, not so much. What is the domain of natural log? Very good. So I have to be careful that the domain of function f is 0 to infinity. Not start looking at negative 4, because that would be a terrible mistake. The other thing that I need to write is that f is continuous on the interval 0 comma infinity as a sum or also difference of continuous functions. So here I would like to refer back for a second. We did not write this theorem. It's time for us to write it right now. There is an H in there, tiny one. Theorem. Any combination sum difference product ratio, that's what I meant by combination, of continuous functions is of course any combo, addition, subtraction, multiplication, division, of course on their domain. I should be specific, right? Because if x is continuous and 2 is continuous, of course, but 2 over x, the ratio is not continuous everywhere. It's not continuous at 0. So I should put in parentheses at least any combo of continuous function is continuous on its domain, on their domain. So for example here, natural log is continuous on 0 to infinity, but 2x is continuous everywhere, and negative 3 is continuous everywhere. But I have to restrict the domain because of natural log. Okay, so now let's find these values where there is a c. We have to put in the calculator. So let's put the function in. So in y equals clear everything you have. And let's put in the function natural log plus 3x and minus 2. And go to second and table. Of course, I can plug in 0. The 0 was there from a different problem with my other students, or from, yes, with a different problem. Okay, so let's say I'm going to put in 1.
Wasn't it 2x minus 3?
What did I put?
Yeah,
Oh, I'm sorry. Thank you. It wouldn't be nice. Thank you, my error. Okay, so I'm going to put in 1. I'm going to put in 2. And I'm happy. So we normally look for at least a 1 unit interval. If you tell me that there is a solution between 1 and 10, I will not, that doesn't mean anything. So, but if you tell me there's a solution between 1 and 2, yeah, I will consider that perfect. So I'm going to write that the interval in which we are looking for is 1, 2. I have to write as number 5 that f of 1 is negative. I don't care for the number. And f of 2 is positive. And as a continuous function that changes sign between, is that okay?
How did you put those two back together?
I just started with 1, and then I continue with 2, and then I continue with 3, and then with 4, whatever, till I hit an interval where the function changes sign. So it was negative at 1 and positive at 2, and that's good enough for me. It may have 10 other solutions. I don't care. I'm not asked to determine all of them. I'm asked to find a solution.
In general, what's that?
Oh, you can go as close as you want. You can use a left and right, or 0.1 or 0.2. Yeah, but this is good enough. A 1 unit interval is all we need. You'll see what happens in chapter 4. You're not going to need more than that. So then I will say, by intermediate value theorem, there exists a C in the open interval 1, 2, such that f of C is. So we found a solution. To be exact, we found an interval where a solution is. We did not find a solution. We know there is a solution between 1 and 2. But what is it? We do not know. And that's not what the theorem is good for. The theorem, the intermediate value theorem, is supposed to tell us where to look for a solution. At least not wider than 1 unit interval. Any questions? Fair enough? Good? Easy enough? Eric, you want to say something? Go ahead. Is this okay? Say it again.
I'm just observing it.
But is there a problem?
No.
Because I'd like to address it if there is. Any questions?
To be sure.
Yes?
This by theorem, that C is some constant, right?
It's a solution, yes.
Okay.
Yes, it's a solution. So that f of c is 0. F of 1 point blah, 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 blah is 0. But I can determine it right now. I have to wait till chapter 4. We're going to apply Newton's method. And we're going to find a solution with any accuracy you want. 10 digits if you want.
So you couldn't just solve for the solution right now?
You can, but not algebraically. No one can do this by hand.
Like I said, like what is this solution then? Isn't it just finding where the function crosses the x?
Right, exactly. The x-intercept or the 0 of the function or the solution of f of x equals 0. We don't have it.
And you can't set the original equation equal to 0 and then solve it. You can't do that.
This is what we did. We did that from the very beginning.
No, yeah, yes.
But you can solve this by hand. Give it a shot. How will you solve this?
I guess I don't know.
No,
Okay.
there is no way. What you can do is to plug in the graphing calculator and try with a graphing calculator to determine a solution. You will be able to, but you have to graph it and just use the
So
the 0 feature, and you will get an approximation of the solution.
so all this does is just say, yeah, there is a solution.
Exactly, exactly. It just tells you, it points you in the right direction and saying you're looking for a solution, make sure you look between 1 and 2. Yeah, and using this, we're going to apply Newton's method. After we find the interval, we will be able to use Newton's method and find the solution exactly with as many digits as we want. 10 accuracy, 5 accuracy, 11 accuracy, whatever you want. On any equation that prior to this we were not able to solve algebraically. Good. This theorem just says if the function is continuous and it changes sign on that interval, there must be a root there between 1 and 2. That's all it says. What is it? It does not tell us. It can't. It only says look for it right here. It's somewhere between 1 and 2. I cannot even tell you if it's closer to 1 or closer to 2. I have no idea. Somewhere. But you will definitely find it between 1 and 2. Any questions? Any questions?
I think your video hit now.
I'm sorry?
Your video hit now.
It's still, no, it's 33. Thank you. It's working. I sometimes look because it happened in the past a couple of times. It did not record. Okay, good. So the next in line is 2.6, in which we are talking about limits at infinity. Okay, let's discuss two situations in which the second one, of course, when we say limits at infinity, it could be negative infinity, it doesn't matter, and infinite limits. And what's the difference? Here's the difference. The first example is limit, let's say, as x approaches 1 from the right, from 1 over x minus 1. 1 from the right is 1.1. This is 1 over 0. It does not exist, so this will be infinity. So this is, the result is an infinite limit. Therefore, x equals 1 is what? For this function?
Very classes.
Excellent. This is one thing that we knew already. Okay, let's talk about this. This is a different story. This is limit when x approaches infinity or negative infinity. For example, from 1 over x. What do you think the answer is? Right, which means y equals 0 represents what? Exactly. Now, the first limit, when the answer is infinity, we're thinking in terms of vertical asymptote. The second one, when x approaches infinity or negative infinity, we're talking about the endpoints or end behavior. If that is 0 or 5 or 10 or 1/2, then that will be y equals 1/2, y equals 0, y equals 10, whatever I get here, horizontal asymptote. So be careful, because sometimes we will write at infinity only, because it's possible that functions that we haven't looked at before in pre-calc, some functions will have a horizontal asymptote to infinity at, let's say, y equals 2, and to negative infinity, let's say y equals negative 2. It doesn't have to be the same asymptote on both sides. So functions, we can encounter that, and we will. So I may have to say at infinity only, but this is a rational function. It doesn't make any sense. So it's going to be the same. So if the limit of 1 over x as x approaches infinity, and we know the graph, right? There is no ambiguity there. This is the graph of 1 over x. So as x approaches infinity, the function values approach 0. As x approaches negative infinity, the function values approach 0. There is no discussion there. Now, what will you tell me about the limit of 1 over x to the power r when x approaches infinity? And we say r is a positive rational number. What will you say? Because if it's negative, the situation is different. It will change. It will come back to the top. But if it's positive and stays in the denominator, the expression x to the r power stays in the denominator. What is the answer then? Of course. So please keep this in mind, and let's practice. So please choose. We're going to look at a example also of a function with a given such and such. So you can choose from the handout. You can choose from your book. Let's take a look at these limits. Anything you like. There are many and different types, of course, again. So I recommend we should start with something like 16 or 18 and then build our way slowly but surely towards the bottom. Okay, so let's start with 16. So 16 on 141. Limit as x approaches infinity from 1 minus x squared, everything divided by x to the third minus x plus 1. Yes, that's what it is. Okay. Coming back to our indeterminate cases. Oops. Coming back to our indeterminate cases, how many indeterminate cases did I mention we have? 7. What was the first one that we looked at? This will be the second one. We're going to add on. Okay, so obviously we're asked to determine a limit. We're going to have to plug it in, and you'll say again you're not allowed to, and I'll say I know you're sure you're correct, but I have to because I don't know what I'm facing. Maybe this limit is 5, and I'm done. I move on. But if it's 0 over 0 or something else, then I have other alternatives. So where does the numerator go? Careful. It's not that it matters, but yes, it's negative infinity. Where does the denominator go? These are too small to mention. Good. So this is our second indeterminate case. We don't know what the result is. Indeterminate case. We have no idea. So this is our second one so far. Perfect. So then I look at the numerator, and I'm going to ask you what is the degree of the numerator. It is 2. Since it's a negative leading coefficient, I will rewrite it as negative x squared plus 1. And please factor out the degree with the negative leading coefficient. What is the degree again? 2. So I have to factor out x squared. And you could say, you can't. X squared is not a common factor. I would have to agree. It's not. I'm going to force it. So negative x squared times what is negative x squared? 1 minus. Negative x squared times what is 1? So negative x squared times negative 1 over x squared is 1. Ready for the denominator? I can factor out anything I want from anything as long as what it's in parentheses allows me to go back to where my starting point was, right? So negative x squared times 1 is negative x squared. Negative x squared times negative 1 over x squared is 1. What is the degree in the denominator? Good. I'm factoring out x cubed. Again, you could say, wait a minute, x cubed is not a common factor. I would have to agree. Please give me 3 terms so that x cubed becomes a common factor. Yes, of course. Yes. Excellent. Excellent. That's it. Very good. Now my next step is this. Can I simplify x squared from the top with x cubed from the denominator and still have an x in the denominator? Would you agree with that? Good. Next step, I'm going to ask you, where is this going when x approaches infinity? Yes, we just discussed that. Very good. Where does this go when x approaches infinity? Where does this go when x approaches infinity? Where does this go when x approaches infinity? Exactly 1 over 1, which is 1. But now, where does negative 1 over x approach or go when x approaches infinity? Exactly. So the limit is 0. Sorry, I did not plan correctly. Any questions? Actually, this is what we did in pre-calc to determine the horizontal asymptotes, but we didn't tell you that. Since we are determining when x approaches infinity, when I determine the limit as x approaches infinity from this function and we got 0, obviously y equals 0 must be a horizontal asymptote. I'm not going to write at infinity only because this is a rational function. For anything else, I will write at infinity only. But this is very clear, it's just a rational function. Questions?
The green one, the green square, you had it pushing what?
No, I simplified x squared divided by x squared is 1, and x cubed divided by x squared is x.
As you were kind of circling the different components,
Yes.
You had.
When x approaches infinity, this approaches 0, this approaches 0, this approaches 0.
Then you drew the bigger box.
Yes.
On the bottom right, you have.
Yes, 1 over 1. But then there is a 1 over x in front. And 1 over x times 1 is 1 over x. And when x approaches infinity, 1 over x or negative 1 over x will approach 0. Better?
Yeah.
Perfect. Good. We need to practice. Anything catches your eye? Let's also do 18 before you choose the next one. So let's take a look at 18 as well. Still on 141. And 18 is limit as x approaches negative infinity from 4x to the third plus 6x squared minus 2 divided by 2x cubed minus 4x and plus 5. Because you had questions, I think it's better if we do one more like this.